Good afternoon, everyone, or good morning, depends on your location. Welcome to another TACO-sponsored webinar. My name is Brett Zerba. I'm an applications engineer with TACO. I will be the moderator for today's presentation. Rich Medeiros. Most of you have been on these, so you kind of know the routine, but Rich Medeiros will be doing the main presenting today. Before we get too far, if you wouldn't mind raising your hand, let's do our hand raise just so you can see our screen. And okay, good. I see Scott and Sean and others have raised their hands. So I'm sure you can see Rich's screen and you can hear me. And you'll be hearing Rich very shortly. TACO, 100-year company, headquarters in Cranston, Rhode Island, worldwide. Johnny White, the White family owns it. Cheryl Merchant leads his team of senior management. She's the worldwide president, if not a higher title. I always get confused on titles. I barely know my own. Today's presentation is on pump selection in NPSH. And this topic, especially the second topic, lends itself to some questions. And really, we would like to open it up if you've ever had some NPSH issues. Rich and I and others can learn from some of the potential issues that you've had in the past. So please feel free. So just type the questions in when you get time. Steve says hi, so I know the questions section's working. So that's a good sign. And there are no handouts. And just to clarify, this is a 6-week course, and this is week 3 of 6. So there's 3 more after this one. Same time, same place. And then after the 6th one, you will be getting an email with access to your 6 PDH hour credits. If there's an issue with that, send me an email or send us an email, and we'll try to work with you. So keep that in mind. And also, I had showed at the beginning, I was showing a screen that showed where the videos are. After class 6, you'll get an email with all 6 videos, but there is a YouTube channel, a TACO YouTube channel that has the videos posted a day or 2 after each class. So classes 1 and 2 are already available, and class 3 will be available by a couple of days from now. Today's Wednesday, so just keep that in mind. So anyways, other than that, I think we're ready. I'm ready to turn it over to Rich. Rich does a great job in this presentation, and I'll let him do some more introduction of himself. So take it away, Rich.
Thanks, Brett. Hopefully, Brett, you can hear me okay and you can see my screen.
Yes, sir, I can.
Great.
Loud and clear.
So a quick introduction for myself. Again, my name is Rich Medeiros. I'm one of the senior systems engineers here at TACO. I specialize in engineering and design of HVAC systems for commercial buildings and institutional and industrial. I spent most of my career on the design side working for consulting firms. And I've been with TACO for almost 8 years. Wow, Brett, I can't believe it's been 8 years. It feels like I just walked in the door yesterday.
Isn't that amazing? It's just amazing.
It's amazing.
It really is.
So today we're going to talk a little bit about pump selection and NPSH. NPSH stands for net positive suction head, and we'll get into those definitions in a couple of minutes. So without any further ado, as they say, let's talk a little bit about what we're going to cover in this first half: pump selection, NPSH, selecting a commercial pump, how to read a pump curve, NPSH, and then questions at the end. I actually have 2 slide presentations, and I'm going to switch to the second presentation when we get to the NPSH topic. So I have a little diagram of an HVAC system on the screen right now, and we're going to focus our attention on the condenser water pump. So let me grab my pen, my drawing tool, see what kind of colors we have. I think I'll make it red today. So with a little luck, I'll grab the pen. There we go. Okay, so we are going to focus our attention on selecting a pump for the condenser water side of the system. So this is a water-cooled chiller. and this is the condenser water side over here. Just for general reference, on the left side, this part of the system is the chilled water side. So we're interested in making a selection on the condenser water side. So someone has already designed the basic system. They've figured out what the pressure drop calculation is and what the flow is. And in this particular case, it's 1,488.4 gallons per minute at 50 feet of head. That's what the pump selection is going to be based on, but we're going to round that up a little bit. We're going to take those values and I'm going to make a note up here just initially so we'll know what we're making a selection for. So I'm going to round that off to 1,500 gallons per minute. Round that off, 1,500 GPM. You kind of bear with me. Drawing with a mouse is not the easiest thing in the world. And 50 feet, so to make sure I have enough pressure available, I'm going to make that 60 feet of head. So that's what our actual selection will be based on. And because this is a condenser water pump, this cooling tower that we've shown over here on the right, this is an open cell cooling tower. So it's open to the atmosphere. And we're not going to be too concerned about that in our initial process, but when we get into the net positive suction head part of our discussion, we'll talk about that in some detail. What's important to realize is that the center line of the pump, roughly down here somewhere, is at a lower elevation than the water level in the cooling tower. So if the water level in the cooling tower, let's kind of make an arbitrary line here, and this is the line for the center line of the pump. That vertical distance, we want the cooling tower to be physically above the center line of the pump. And that vertical distance is going to be important. You'll see that when we get into the actual calculations a little bit later. So that's just to orient everyone and to understand that we're going to make our selection based on 1,500 gallons per minute and 60 feet. So before I go any farther, are there any questions about this initial diagram and the pump selection we're going to make?
Nothing posted, Rich.
Okay, so we're going to do 1,500 gallons per minute at 60 feet. So I'm going to, a little luck here, go live on our TACO website. So if we go over here and we go to our TACO website, I'm at the home page. And on the left-hand side, about halfway down, you see the word apps. I'm going to click on that. And then the next drop-down menu, third item from the top, pump selection. And now I'm into the TACO pump selection app. And in this case, it's a 4-step process. The first step is to decide the pump type. And I can choose between OE, which stands for optimized efficiency. I can go for self-sensing variable speed pump or standard pump. For today's selection, I'm going to look at a standard pump. And step 2 is where I get to put in the flow. And we said our pump needs to be 1,500 gallons per minute at 60 feet of head. Now, where it says minimum efficiency, I like to leave that at 0. If I put a value in, for example, maybe I put in a value of 80%, I will only see pumps that have an efficiency of 80% or higher. Now, at first glance, you might say, well, that makes a lot of sense. Why don't we do that? Well, if I put in an efficiency value, then I won't see all the selections the software has to offer. So I usually leave the minimum efficiency at 0 so I can get an idea of what's out there for pumps that will provide what I'm looking for. And if you recall from our little diagram, it was an end suction pump. So for option 3, before I get into end suction pump, here's where I determine the fluid. And in this case, I can say select fluid below or enter custom fluid options. I'm going to leave it at the default value of 60 degrees Fahrenheit. The RPM, I have a choice. If I'm running at 60 Hertz, the RPM is either 1160, 1760, or 3500. And again, I'm going to leave it at all so that I can see all the selections the software has to offer. I'll leave the units in US. You also have a choice to switch to SI, which is basically the metric system. And the thumbnails will be based on performance. And in this case, I have also one pump. So I'm going to now go to step 4, click on end suction pump. I want a frame mounted, so I'm going to deselect the CI, which stands for close coupled, and then click on search. Now, as you can see on the right-hand side, I'm going to zoom out just a little bit. The right-hand side of the screen is you see all of the options the software has to offer. I'm going to shut off my email so I don't get interrupted anymore here. Okay, so if you'll notice, the pump selections have been sorted, and there's a little triangle here next to the letters EFF, which tells me that they've been sorted from highest efficiency. So in this case, the highest one is 86% down to the lowest, which is 56%. Now, these tabs at the top, you can click on them and you can change the order of the sorting. So if I click on EFF, it'll actually now sort it from lowest to highest. So you can see the first one is 56 and the last one is 86. And you can also sort on any one of these fields. So for example, if I'm interested in the net positive suction head, I can click on that and it'll sort it from lowest to highest. So let's go back to efficiency, and I want to sort from highest to lowest. Triangle is pointing down. I look at the thumbnail and I'm kind of taking a quick look, and I kind of like the one second from the top. And that's model FI6009D as in David. I kind of like that one. So I'm going to click on that. And now I'm going to zoom in a little so you can see initially I get this narrative data. And here's that flow, here's that flow again, 1,500 gallons per minute. Let me get my pen over here. 1,500 gallons per minute at 60 feet of head. That's the original design point. I've selected a pump that's running at 1760 RPM. It happens to have an 8.7-inch diameter impeller. It's an 8x6 pump. That means that the inlet size is 8 inches and the discharge size is 6 inches. It's 86% efficient. The horsepower is 26.42 at the duty point, at the design operating point, which is this point up here. That corresponds to this horsepower here. And the maximum horsepower that this pump could possibly consume operating at 1760 RPM and 8.7-inch diameter is 28.83. So that's what non-overloading horsepower refers to. NOL stands for non-overloading horsepower. And in this case, the net positive suction head is 21 feet. And that's what the net positive suction head is required by the pump. So I'm going to zoom in a little so that you can see the pump curve. Let's move out just a hair. There it is. So there's the detailed pump curve. There's our design operating point, 1,500 gallons per minute, 60 feet of head. Repeating, there's the 1,500 gallons per minute, 60 feet of head over here on the left. Where those 2 points intersect, that's our design operating point. So let's look at what information the pump curve is telling us. The red line is the actual pump curve based on the impeller diameter that we just looked at. Just as a reminder, let's go back and see what the impeller diameter was. Impeller diameter is 8.7 inches. So you can see from here, I have an impeller diameter of 8.7. This black line right here is 8.5 inches. So the impeller is slightly larger, so it's moved up in this direction. So the red line represents 8.7. Did I just say 8.7, Brett? 8.7, yes.
Yes, you did.
All right.
We have
8.7 inch diameter.
we have a relatively simple question, Rich.
Yeah, shoot.
So this is a FI, which is a base-mounted pump, and somebody asked if is it common for the suction and discharge? You said 8x6 to be different diameters or different sizes. I guess I should say.
Yes, in most end suction pumps, the inlet size is larger than the discharge size. Now, if it was an inline pump, and the name inline implies that it's connected to a straight section of inlet and outlet pipe. In that case, inline pumps have the same inlet size as the outlet size. But for end suction pumps that typically have a larger diameter at the inlet than they have at the outlet. That's a great observation.
Thank you. I'm sure that answered his question.
Okay, so what's the other data that we can see on the pump curve? We can see these dotted lines. These dotted lines here are lines of constant motor horsepower. That's what the electric motor can provide. And this one starts at 20 horsepower, and you can get, in this particular configuration, up to a 40 horsepower motor. Our design operating point is just above the 25 horsepower line, and if you'll notice, the red line, which is our pump curve at 8.7 inch diameter, follow that all the way down to the end. It never crosses the 30 horsepower line. So a 30 horsepower motor would be the appropriate motor size for this selection. Then we have these curved lines. These are lines of constant efficiency. And we have a special value over here. This is the maximum efficiency that this pump could possibly produce. And that's called the best efficiency point, or BEP. So let me just write that up here. BEP stands for best efficiency point. How to get that in there. And that refers to this efficiency, which in this case is 88.5, that only occurs at the maximum impeller diameter for this given model pump and this given speed of 1760. So for every model pump at a given speed, they have unique best efficiency point, and that always occurs at the maximum impeller diameter. And then the last value on the chart here would be the NPSH required by the pump, or the net positive suction head required by the pump. So if I follow that 1500 GPM line vertically upward, you can see the chart at the top where it crosses this curved line right here. That is the net positive suction head required by the pump, and it looks like it's roughly 21 feet. So I'm just going to write that number up here, 21 for a moment. And that represents the net positive suction head required by this pump, 21 feet. Not the best lettering in the world, but hopefully you get the idea. Just to make sure, I'm going to go back to the narrative data and see that it was, yes, in fact, 21 feet. Okay, so we can see that we can see the flow on the horizontal axis, the differential pressure in feet of water column on the vertical axis. We can see the red line, which represents the impeller at 8.7 inches. We can see the blue line, which I haven't mentioned. That's called the system curve, and that's characteristic of the system. We talked about the best efficiency point, the lines of constant efficiency. So this selection falls on 86%, so that's an 86% efficient pump. And then we can find the required net positive suction head by reading it off the chart. Any questions before we move on to the net positive suction head discussion?
Yes, we have a couple ones here. Does the app plot the system curve based only on the pressure drop of 60 feet? What other variables determine the system curve shape and slope?
Well, the system curve is always, in a closed loop system, is always at 0, 0. In our case, we have an open loop system, but we haven't decided what the vertical distance is. So for now, I'm assuming that our vertical distance is 0 between the center line of the pump and the cooling tower. When we get into the NPSH calculation, I'm going to actually estimate what the vertical distance is between the water level and the cooling tower and the center line of the pump. So once you establish a design operating point, in our case 1,500 gallons per minute at 60 feet of head, you can apply a simple equation, which we're going to see. Actually, do I show it? No, I don't show it in this presentation. It basically says that the ratio of the flow squared times the initial pressure is equal to the final pressure, and that's how you generate the system curve. So the system curve is generated mathematically. We actually don't take any measurements. It's kind of a theoretical curve, but it does represent the relationship between flow and head in your particular system. Any other questions?
What other fluids does the app let you use for selection?
That's a great question. So I can go back. Let me erase all these lines for a moment. When I went through my selection process, I initially made it water because I knew it was condenser water. Well, let's assume that for a moment it was a closed loop and it happened to be a chilled water system. And I could, under select fluid below or enter custom fluid options, I could click on enter custom fluid options, and this little dialog box opens up. And I could select, for example, propylene glycol. I could have a temperature of, say, 42 degrees and a concentration of perhaps 40%. Then I click on get specific gravity, then click on search, and now not only will I have the pump selection, but I'll also have the characteristics at that glycol solution. So this chart right here shows the pump curve, which is in red, and it shows the 1,500 gallons per minute. Let me get my pen over here. It shows the same we had before, 1,500 gallons per minute, 60 feet of head over here where those 2 points intersect. That's this point here on the red line, and that's 8.7-inch diameter. But it also shows the horsepower with the new solution. The horsepower at that duty point is 27.6. And if you recall, when we went back to the original, let's go back to the original selection. Let me just erase those lines for a second. In the original selection, I believe the horsepower was a little bit less than that. Yes, it was around, what was it, around 26, I think?
Yes.
And then in this case, it's actually 27.6. So the horsepower has increased as a function of the fluid that we've chosen. Any other questions?
Actually, there's a pretty good question. When you inputted on the first screen the flow and head, you got 5 or 6 different pump selections. How do you choose the one that you choose?
That's a great question.
Yeah, it really
Let's go back to the.
Hopefully, I got it out correctly. I apologize. I kind of.
Yeah,
But anyway,
let's go back.
Yeah.
I'm going to change the fluid back to the default value of water at 60 degrees Fahrenheit. And then make the selection so I can go back to the original selection that I made. So I'm looking at these thumbnail sketches, and on my computer screen, by the way, I can make out the lines reasonably well. In terms of broadcasting over the internet, I'm not sure if the thumbnails are clear enough for you to see. Maybe Brett could kind of comment on it. Can you see the curves in there, Brett?
Yeah, I mean, they are a little cloudy without popping in.
Yeah. So what I'm doing is I'm initially looking at the shape of the curve. I know from experience, I'm going to select that one again, and I'm going to go back to the thumbnail so you can see. So here, if you'll notice, the BEP is 88.5, and I want to be, if you think of dropping a vertical line, let me try dropping a vertical line for a moment. If I drop a vertical line from the best efficiency point down to the flow line, it's not the best drawing in the world. So we know that's 1,500, that's 16, 17, 18, 19, 2,000. So it's just under 1,600 gallons per minute. That's the best. At the 1,600 gallons per minute, I'm going to get the highest efficiency possible. And so I want to be as relatively close to that BEP flow value as possible. So when I look at the thumbnail, I can actually see, let's erase here a little bit. So when I look at those original thumbnails, I can see, it's hard to see perhaps on your screen, but I can see where the BEP is, and I want to be relatively close. I also want to be midway up the curve. So if I go over here, when I say midway, let's go back to the curve again and zoom out just a little bit. You can kind of think of the curve divided into 3 parts. So this is the upper left. There's the middle kind of, and then the lower right. So roughly I'm not doing the best job in the world of drawing bubbles, but I want to be roughly in the middle third generally. So I want to be close to the flow associated with BEP. I want to be in the middle of the curve, and I want to be as high up on the efficiency line as possible. So when I look at those thumbnails, that's what I'm actually looking for. Let's get rid of this erasing thing. So going back to the thumbnails one more time. See, the first one is way down in the efficiency. I don't like that one. The one I selected, I kind of like that one. The third one down, I'm relatively high to the efficiency, but I have no place to grow. In other words, this pump here, the FI 6009D as in David, has, I believe we said, an 8.7-inch diameter impeller, and I think it has a maximum impeller diameter somewhere around 13 inches, maybe a little bit less than that. Hold on one second, let me just go back. 9.5. So in other words, if I had to increase the capacity of that pump, I have some growth here. But this one, it's almost at the top of the curve, so I don't have much growth. The next one down is a little bit too far to the left. The next one is too far to the right. The next one's way too far to the right. And the last one's way too far to the right. So by quickly looking at, and when you do this day in and day out, you can zoom in on the thumbnail. That's why we offer the thumbnail, so you can kind of get a snapshot of all these different shaped curves. Usually you can zoom in on the one that's the best selection pretty quick. Hopefully that answers that question, Brett.
Great answer.
Any others before we move on?
One other one. Why is the system curve parabolic?
Why is it parabolic?
Yeah.
Well, it's parabolic because of the general equation, which...
Y equals x squared, right? Yeah.
Right. Well, it's actually y equals ax squared. And if you look at a polynomial where it says that y equals ax squared plus bx plus c, we actually don't have the bx and the c term. And if you cross out those two terms, and you have y equals ax squared, where a in this case is the initial pressure, x is the ratio of the flows, so the ratio of flows squared times the initial pressure is equal to the final pressure. That essentially is a parabolic curve. Now, the reason we only see the right half of the curve is because we only plot positive values for the ratio of the flows. We don't plot negative values. And that's why it's the right half of a parabolic curve. Hopefully that answered the question.
I'm sure it did. Let's move on.
Okay, so now let's go into our second part of our discussion, and that's the introduction to net positive suction head. So I always like to start off with a little list of things we're going to cover in this one. So we're going to say, well, what is net positive suction head? What's the Goldilocks planet? Properties of water, how to find Npsh required, how to calculate Npsh available, and questions at the end. We're doing really good. We're about 30 minutes left, and I think we're in excellent shape for timing here. So by definition, what is Npsh? Well, it stands for net positive suction head. And when we're talking about head, we're talking about in this case, the pressure at the suction side of the pump, and specifically in feet of water column absolute. So all of these pressures are absolute pressures. And then the definition, the net positive suction head for pumps can be defined as the difference between the liquid pressure at pump suction and the liquid vapor pressure expressed in terms of height of liquid column, and in our case, feet of liquid column, since we're using US units. And again, net positive suction head R, or NPSH R rather, equals net positive suction head required by the pump. And NPSHA is the net positive suction head available from the system. We're going to get into this in a little more detail, but that's what the terms mean, and that's where they come from. Okay, what do we mean by the Goldilocks planet? Well, if you're familiar with the fairy tale Goldilocks, Goldilocks is a young girl who's walking through the woods, not really sure what she's doing in the woods, but anyway, she comes across the bear's house. I'm pretty sure by today's standards, if she goes in, that's called breaking and entering. So, but she manages to get into the house, and what does she see? She sees porridge. And the first thing she figures out is that the first bowl of porridge is too hot, the second one is too cold, the third one is just right. So in terms of temperature, our planet Earth is not too hot relative to liquid H2O. And the word we use for liquid H2O is water. And water, or liquid H2O, or H2O in its liquid format, stays liquid for roughly 90% of, I'm sorry, for 70% of the planet is liquid H2O. And that's because the planet is not too hot, the planet is not too cold, and the pressure is also just right. That's what we mean by the Goldilocks planet. So when it comes to liquid water, or H2O liquid or water, it stays as a liquid because of its temperatures and its pressures. So let's go a little bit farther. How to find net positive suction head required? Well, that's the easiest value to find because every pump manufacturer publishes the net positive suction head required by the pump on their pump curves. So here's one, not the same values that we had a few minutes ago, but here's just a pump curve. And just like before, in this case, it happens to be 2,400 gallons per minute. I follow that line vertically upward, and where it intersects this other line right there, that's approximately, I'm going to say that that's approximately 26 feet. So how do you find net positive suction head required? It's always on the pump curve, whether it's our pump curve or someone else's pump curve, they always publish that data because it's very critical, especially when it comes to open loop systems like we're going to demonstrate today. Okay, so now let's erase all that wonderful stuff. Let's talk about net positive suction head available. But before we do that, we have to talk a little bit about, I bring up my whiteboard here. I was doing some calculations earlier today, so let's clear that out. Okay, we have to talk a little bit about the properties of water. So I'm going to draw an imaginary container. Here's my imaginary container. It's open at the top. Looks like a little pot. And it's partially filled with water. So this is water down here. And it's open to the atmosphere. And we're going to assume that we are at sea level. Sea level. Make it simple. And if we are at sea level, if anybody wants to type this in, be my guest. I'll tell you what the value is. But anybody know what the absolute pressure in pounds per square inch absolute at sea level? Anybody wants to type that into the questions area, see if anybody knows what that value is. While I'm taking a quick look at your question, someone said around 13 PSI, someone said 14.7. It turns out it's correct, 14.7 is the right value. 14.7.
1.013 bar.
Excellent. 14.7 pounds per square inch, absolute. And the important thing here is that we're talking about absolute pressure. Now, in the pump world, we measure pressures in feet of water column. So it turns out that 2.31 feet is equal to 1 pound per square inch, 1 psi. So to convert 14.7 pounds per square inch absolute into feet absolute, we would take 14.7 times 2.31, and that would be approximately equal to 33.9. So the equivalent of 14.7 pounds per square inch in feet of water column. And again, in the pump world, we just write the word feet, but we really need to think of it in terms of water column. And in this case, we're talking about absolute pressure. So it's 33.9 feet of water column absolute. So that's what the atmospheric pressure would be at sea level. So if I have my container and my container happens to have water in it that's 100 degrees Fahrenheit, 100 degrees, that's not the best. Can I use my eraser? Let me try my eraser, Brett. Wow, look at that. That is really cool. 100 degrees Fahrenheit. If I have this container and it's at 100 degrees Fahrenheit, if I want to make that water boil, I can add heat. So let's add some heat. I'm going to add heat. And if I add heat, I'm going to increase the water temperature. Remember, it's open to the atmosphere. The top of the container is open. I'm going to add heat. Let's put the word add in there. Add heat. And I'm going to raise the temperature. Does anybody know what I have to raise the temperature in degrees Fahrenheit at atmospheric pressure in order to get the water to boil? Anybody want to take a shot at that one?
I do.
Let's see if anybody types. Yes, first try. 212 degrees. So if I add heat, I have to increase the temperature to 212 degrees Fahrenheit. That's wonderful. Everybody got the correct answer. That's great. You guys are paying attention today. That's a good thing. Okay, now, what if I do not want to add heat? I can still get the water to boil. So let's cross out the heat. Let's change the pen color here. Let's cross out the heat. Let's cross out raising the temperature. I'm not going to do any of those things. What we're going to do is seal off the top of the container. So it's no longer open to the atmosphere. And now I'm going to use a magic vacuum pump over here. I'm just going to label it VP for vacuum pump. And I'm going to evacuate the air that's in this container. That means I'm going to reduce the pressure. And if I reduce the pressure low enough, turns out if I reduce the pressure to 0.94924, I get all that in there, 94924 pounds per square inch absolute, that water will begin to boil at 100 degrees Fahrenheit. Isn't that cool? So repeating, you can get water to boil at a temperature less than 212 degrees Fahrenheit by simply reducing the pressure. In this case, I have a closed container. I put a top on it. I put a vacuum pump in there. I evacuated the air until I got the pressure down to 0.94924 pounds per square inch absolute, and that water begins to boil at 100 degrees Fahrenheit. So before I go any farther, anybody have any questions?
Nope, you're clear.
By the way, there is someone here said add 112 BTUs.
Yes, I see that.
I'm not sure what that means, but we'll continue on. So now I can get the water to boil at that temperature. By the way, where did I get the value for the water to boil? Well, it turns out, I can go over here for a moment and look at some steam tables. Is it this one? Yes. Okay, so what you're looking at now is a chart that's called the properties of saturated steam, sometimes more affectionately known as the steam tables. And the property of saturated steam shows the relationship between temperature, this first column over here, and absolute pressure, which is also known as the vapor pressure. So in other words, if I have a temperature of 50 degrees Fahrenheit and I reduce the pressure to 0.17796, do I need to zoom in? I think I need to zoom in a little, Brett, so that people can see this. Let's see what happens if I try zooming in.
Can see
Hey,
it
look
pretty
at
good.
it. Not bad. Now my
Circled.
little bubbles don't line up anymore. But anyway, you can see that at 50 degrees Fahrenheit, the water will boil at 0.17796. Just for the fun of it, I'm going to scroll down to the next page. Can I scroll down here? I can't scroll down. All right, I'll do it the hard way then. Ah, there it is. Okay, at 100 degrees Fahrenheit, there's that value I showed you, 0.94924, and the units are pounds per square inch absolute. So if I reduce the pressure to 0.94924 pounds per square inch absolute, that water will begin to boil at 100 degrees Fahrenheit. Okay, getting back to our little diagram here. When the water boils, it creates bubbles. You've probably seen bubbles boiling in water. And we have a couple of different names for those bubbles. We can call them bubbles. There's a little bubble right there. We can call them holes, believe it or not. In this context here, we can, and another name for a hole is called a cavity. If you've ever been to the dentist and he looks at your teeth, he or she looks at your teeth and says, hey, you've got a hole in your tooth. Normally, they don't tell you you have a hole in your tooth. They normally say, you've got a cavity, which is a hole in your tooth. So when it comes to pumps, if the pressure at the inlet of the pump, and I will put up a sketch here in a minute, gets low enough, that water will boil at whatever temperature you have and create cavities. And when the bubbles appear and then they collapse as a function of pressure, which I will talk about, we call that cavitation. It comes from the word cavity. So before I make a little sketch of an impeller, Brett, do we have any questions floating out here?
Keep going, sir.
Okay. So I'm going to erase all of this stuff, erase canvas, and then also erase these little handy dandy lines here. Okay. So let's sketch out a cross section of an impeller. So this is kind of a gross cross section of an impeller. Looks a little bit like this. And the inlet of the impeller is right here. And that's also known as the eye of the impeller, EYE. Hey, Brett, it just occurred to me, we could say EYEYO. Oh, never mind.
Yes, you could. We need Joe Matt, though, to help you sing.
Joe Matt to sing. Good old Takeo had a pump, E-I-E-I-O. All right, I'll get carried away. If the pressure is low enough, in our case, let's say we had water entering the eye of the impeller at 100 degrees Fahrenheit, and the pressure got down low enough, 0.94924 pounds per square inch absolute. By the way, if I want to convert that 0.94924 into feet, I multiply that by 2.31, and it turns out it's approximately equal to 2.2 feet. And again, remember that these are feet of water column absolute. If that is true, if that's the pressure and that's the temperature at the eye of the impeller, we will create bubbles. And another name for these bubbles are holes or cavities. Now, this is at the lowest pressure. I'm going to use the letter L. meaning lowest pressure of the impeller. As those bubbles travel through the impeller to the discharge side of the impeller, this is the highest pressure by H here. What happens to those bubbles is they collapse, and that collapsing phenomenon is known as cavitation. Bubbles actually collapse or disappear when it goes from the low pressure up to the high pressure. The bubbles collapse, and that's called cavitation. So we want to make sure that whatever the entering conditions of the impeller are such that the pressure is high enough or the temperature is low enough so it does not start to create bubbles, it does not flash into a vapor, and the bubbles don't collapse. If the bubbles don't exist, they can't collapse, and so the pump will not cavitate. And that is the phenomenon known as a cavitating pump. So before I go on to my little diagram, any questions about that?
There is a question that you'll probably answer shortly. How greater must NPSH-A be relative to NPSH-R?
The general rule of thumb is 10 feet, and we'll talk about that in more detail in a minute. Anything else, Brett?
Nope.
Okay. Going back. Now let's look at, let's go to the next slide here. Now let's look at a little diagram. And here's a diagram of a cooling tower, similar to one I showed you originally. Only in this case, we're going to talk about the actual calculation for determining what the net positive suction head is available. Well, let me get my pen over here. So we're interested in calculating the net positive suction head, NPSH-A, and it follows this equation right here. And this equation simply says that the net positive suction head available is equal to the atmospheric pressure plus or minus the vertical distance, and I'll talk about each one of these terms in more detail, minus the friction, minus the velocity pressure, minus the vapor pressure. So the very first one is the atmospheric pressure. If you're at sea level, you already know what that value is. That's 14.7 pounds per square inch absolute. I do have a chart, which I'll show you in a minute, at what the pressure is at different elevations. This value Hz, the second value here, is the vertical distance. And the reason that's plus or minus, we want the pump to be always below the water level in the open cooling tower. This is a cooling tower that's open to the atmosphere. And if the pump is below that, then that vertical distance is a positive. So that's a positive or +5. We never want the pump to be above the cooling tower, but if it was, we'd have to use the negative value. So in most cases, hopefully if it's designed properly, it should be a positive value. HF is the friction, and all that is the pressure drop in the piping system, including the pipe, the fittings, the end suction diffuser, or there might be a basket strainer, anything that's in that piping system between the water level inside the cooling tower and the suction side of the pump. Remember, we also have to take into consideration the end suction diffuser. The next value is the velocity pressure. We have to subtract out the velocity pressure. And let's take a quick look at how you calculate velocity pressure for a moment. So we calculate velocity pressure. Let's go back to my whiteboard. Erase that for a moment. So the velocity pressure, let's use a black marker this time. So the velocity pressure, sometimes people write it as V sub P, is equal to the velocity squared divided by 2 times the gravitational constant. And all of these have to be in the same unit. So right now we're going to use US or imperial units. So the velocity, let's arbitrarily pick 8 feet per second. So we'll put an 8 in there. Let's say our velocity is 8, and this is FPS, feet. Whoops. Well, I screwed that up, didn't I? Let me try erasing this thing here. Make it a little bit easier to read. So we'll say that it's 8 feet per second, FPS, FPS, and we're going to square that, and we're going to divide that by 2 times the gravitational constant. And the gravitational constant in imperial or US units is 32.2 feet per second squared, SEC, squared. So if I do the arithmetic out, I'm going to get 8 squared is 64, and the units are feet squared per second squared. And then the denominator, 2 times 32.2 is going to be 64.4, and the units there, just like over here, is feet. Oh, I'm sorry, it's feet per second. Yes, feet per second squared. So that's feet per second squared. So second squareds cancel. Feet down here cancels, and the square up here cancels. So you would get approximately 64 divided by 64.4 is approximately 1. And I know it's not exactly 1, but I'm just going to round it off. Say it's 1 foot. So if you have, that's the velocity pressure we just calculated. If you have a velocity, whoops, of approximately 8 feet per second, then your velocity pressure is going to be approximately equal to 1. And the reason I pick that 8 feet per second is because that's generally the maximum pressure that the maximum velocity that you would like to have on a condenser water system at the inlet of a pump. So if the velocity is higher than that, the velocity pressure goes up exponentially. If it's lower than that, it's going to go down exponentially. Any questions, Brett, on velocity pressure?
Nope.
Okay. So we're back to our diagram. Hold on, there's our diagram. Back to our diagram. So now we have all the values that we need, and we just said a minute ago that the vapor pressure, which is our last term over here, is equal to 0.94924, which is approximately equal to 924 times 2.31, again, that's approximately equal to 2.2. So if I just simply plug in those appropriate values into that equation, it looks like this. And those values are 33.9 plus 5 feet, that's the vertical distance. The pressure drop is estimated at 5 feet. The vapor pressure, the velocity pressure at 10 feet per second is 1.6 feet, and the vapor pressure is 2.2. I just simply looked it up in the steam tables at 100 degrees Fahrenheit. So therefore, my available net positive suction head available, if I do the arithmetic out, is 30.1 feet. The pump I selected needs to be at least 10 feet below that. In this case, I selected a pump that has 18 feet. So I could have picked a pump that's roughly 20 feet and it would have still been okay. So that's how you calculate the net positive suction head available. Compare that to what's required by the pump. The available pressure always has to be greater than the required pressure in order to keep the pump from cavitating, in order to keep the pump from creating bubbles at the eye of the impeller and having those bubbles collapse, which is cavitation. And cavitation is not a good thing. When a pump is cavitating, it sounds like it's pumping marbles. Some people say it sounds like it's pumping ball bearings. Some say it's like sand, rocks. It's a very distinctive sound, and it can be very, very loud. And it will, in time, destroy the impeller and then eventually the stationary part, which is the volute. So today we've gone through selecting a pump, calculating, not only selecting a pump, but identifying the net positive suction head required by the pump, and also how to calculate the net positive suction head available. So now, any questions?
We have a couple questions. Yes, we do. What would happen if the piping is underground? I guess someone's asking, can you show what would happen if piping was underground with this same graph? I guess it really just affects the height, right?
Yeah, remember what you want, because one of the terms in this little calculation here is the vertical distance. That's this HZ value. So the greater the vertical distance is above the center line of the pump, the higher your net positive suction head available will be. So you can accomplish that by, one, increasing the height of the cooling tower or lowering the location of the pump. Now, another way of doing it is, instead of using an end suction pump, you could use a vertical turbine pump. Vertical turbine pumps usually sit right on a pad in the mechanical room floor, and the actual pump section is below that, way down here. This is the pump inlet is way at the bottom, and you put a can around that. And now you can run the suction piping into the can, and then the discharge of the pump would come out here and then connect to this piping up here. So you can either lower the pump, you can either raise the tower, lower the pump, or you could put a vertical turbine in, which will allow you basically to lower the suction. Now I'm lowering the suction way down here. So if I had 5 feet here and I had 10 feet over here, then my vertical distance would be 15 feet, and that's what I'd put in my equation. So essentially, I would increase my net positive suction head available by 10 feet. So instead of 30 feet available, I would have 40 feet. Any other questions?
Yeah, we have 2 or 3 associated with how does it affect in a closed loop system? Can you still get NPSH in a closed loop system?
Yes, you can have problems with cavitation and not have sufficient pressure available in the closed loop system. Typically, that shows up typically in a hot water heating system when the pump is at the top of the buildings, perhaps in a penthouse, and there's not sufficient pressure to keep the water from boiling. I had a situation, I think it was about 3 years ago, where a new pump was installed in an existing building and the pump was cavitating. And it turns out that the hot water heating system was operating at 200 degrees Fahrenheit. The NPSH, the pump that was physically selected for the job, someone did not do the calculation because they figured it was a closed loop system, so they didn't do the NPSH available calculation. So the required pressure by the pump happened to be 50 feet, and the available pressure was only 20 feet. And since it was an existing building, the building I think was 30 stories tall, the owner of the building was not interested in increasing the overall system pressure because it was an old system, and he was afraid that the increase in pressure would cause the components at the bottom of the building, where the greatest static pressure was, could potentially burst or leak. So the only solution there was to select a pump that had a required NPSH less than 20 feet. So we selected one, I think, that had 10 feet, replaced the pump, and it worked fine. So yes, you can have a problem in a closed loop system, and you always have to do the calculation, especially if you have high temperatures and relatively low pressures.
There's a couple of questions about the pump being above the tower.
Well, it's possible to put the pump above the tower, but we do not recommend it. There's a whole series of issues when the pump is above the water level of the tower. And for the most part, it's extremely difficult to get the system to work and to keep the pump from cavitating. So at this point, it's possible, but I do not recommend it. TACO does not recommend it.
And what if the CW went down underground from the cooling tower and then came back up to the pump, and the pump is still below the cooling tower? I don't know how to, I don't think we can answer that one. That one needs to be clarified.
So are they saying this, Brett, if I had the piping exiting the cooling tower, instead of making the connection directly here, it goes
Oh yeah,
underground,
then
then
back up.
across, and back up again?
Yeah, I
And
think
so
so.
this
Yeah.
pipe doesn't exist
Yep.
above. In general, that's not a problem.
Hmm.
The problem occurs when you run the pipe up. So if you run the pipe up for a minute, let me get rid of erase that. If you came out of the tower, for example, and you did this, and you ran the piping up like this, and then across, and then down, and let's say this piping in the middle doesn't exist, you run the potential of constantly trapping air up here, and that's not a good thing. In addition to that, when the pump shuts off, the water will drain out of this pipe back into the base of the cooling tower, and then when you start the pump, you could potentially have air sucked into the pump. So that's a very difficult situation. If you're going to do that type of piping, you usually have to add additional check valves and isolation valves. It becomes very troublesome, very problematic. So
And,
try to
and
avoid that if at all possible.
unfortunately, sometimes that happens in the field without us engineers knowing it.
So we're at 1 o'clock, Brett. Why don't we
Yep.
take one more question and I'll pass it off to
One
you?
more. This is a great question. One more question. How does cavitation bubbles, just bubbles, cause damage to the impeller?
Well, it turns out that when the bubbles collapse, they actually create a shock wave. So it's like millions and millions of tiny little explosions or implosions inside the water stream. And those little implosions will eat away. It's as if you are bombarding the pump parts with sand, like it's like using a sandblaster. And when you look at an impeller that's been running cavitation for a period of time, it just literally eats away at the impeller. And if it's very severe, it'll eat away at the volute.
Awesome.
So
I
at
think
this
we're all
point,
set.
I'm gonna turn it back over to Brett, but I just want to say thank you so much for participating in today's presentation. Again, if you have any questions, don't hesitate to send them through their respective rep, and they'll get them over to Brett and I and be happy to answer them for you. So Brett, take it away. Be safe out there.
Thanks, Rich. Great job as usual. And appreciate everyone's thank yous for sure. And again, thank you for your time. We know how valuable that is. We do have another one next week. And other than that, stay safe out there and take care, everybody. Goodbye.